on heterocyclic chemistry. We are discussing the synthesis and chemical properties of azoles. Azoles are five-membered heterocyclic compound, aromatic heterocyclic compounds, and these are of two types. Azoles are of two types containing two heteroatoms. One is 1,3-azoles and another is 1,2-azoles. So in this lecture, we will discuss about 1,2-azoles. Okay. So before going to 1,2-azoles, there are certain important idea about 1,3-azoles. This is the general picturization of or general structure of 1,3-azole. See, there are three carbon positions which are available for different reactions, and therefore reactivities of these three carbon with different reagent would be very much different. These label indicate or tells about the reactivity of carbons. We have discussed these ideas in previous lectures. You can visit that channel and you can watch that lectures also. See, this is the fourth position. If you give number 1 to this Z 1, 2, 3, 4, right, anti-clockwise. This fourth position is what? It is a deactivated by inductive withdrawal by the adjacent nitrogen. You see this nitrogen carbon bond, and here you can find that the nitrogen carbon bond, in this nitrogen carbon bond, what we can say, nitrogen is electron negative and hence it withdraw electron from this carbon, and hence the carbon become deactivated, means no electrons density will be available, hence electrophilic substitution reaction are not possible here. Remember, especially in a five-member ring, this like a five-member ring. Okay, see, if you see here, deactivated by inductive withdrawal by the adjacent nitrogen like a five-membered heterocycle, beta position so activated. And see, if you go for the carbon number 2, is the most strongly deactivated like a pyridine alpha position. If you think about the pyrrole, pyrrole is a what? Five-membered heterocycle, right? And it's a beta position. This is a position number 3. We can say is what? Activated. So activated. Right? Similarly, if you say uh, pyridine, if you think about pyridine, so its alpha position is deactivated. So similarly, these two positions also deactivated because of same thing, because of presence of electron withdrawal.
जिया नहीं आजकल अच्छी लागत है हमको.
Okay. And this fifth position is least strongly deactivated. Okay, like a five-membered heterocycle alpha positions. So these three positions, all the three positions are deactivated, means they have less electron density on them. Therefore, they are resistant to electrophilic substitution reaction at low temperature, normal temperature. But these deactivated three carbon sites are relatively, or when they correlate, we will find that this position 2 is what? Most strongly deactivated, because it is present between the two electron withdrawing group or electronegative atom. Similarly, if you compare these two, so this is most strongly means reaction will not take place here in five-member ring. So reaction either go to this position or this position, and hence, if you compare these two, again, the fifth position is highly means a good reactive compared to this one. Reactivated, least strongly deactivated. So like this, this is the influence of the different uh, influences of the positions of the carbon in these azoles. Okay. See, to understand, there are few reactions are here explained on the basis of the concept just now we have seen. If you think about the electrophilic addition at imine nitrogen, see, if you have taken here, this is what Z can be NH, NR, or oxygen or sulfur, means azoles, all three azoles. imidazoles, thiazole, and oxazoles. So if you uh, react this azoles with what? With the for example, you see here this group. Suppose this you consider this as a any one of these three. So you see the fifth position. This is going at where it at fifth position. So why? What is the reason? This EI means electrophile. EL plus means it is electrophile. And now just now we have seen out of these three positions, only this fifth position is okay, that have a good or logical sufficient significant electron density, and hence we can say electrophilic substitution preferred at 5 position. So remember, whenever we have electrophile and any azole, 1,3 azoles, the reaction will go at what? Fifth position, because out of these three carbon, only this is the preferable positions. Right? Yes. No. Next point. If your aim is to remove the proton from this, and this is NH, suppose, so the proton will be removed from this H and nitrogen, and this will form imidazole anion. And if you add electrophile, then it will go to the nitrogen. So electrophilic substitution reaction takes place at two positions, nitrogen as well as the carbon, that is carbon number 5. So you see, this is basic idea. Fine. Yes. Now see, if this Z is equal to nitrogen, but not with hydrogen, it is with R group or oxygen or sulfur, you can take. So when you want to remove the proton, so which proton will be lost? So remember, second carbon proton going to loss. The reason is what? What is the reason? Because proton removal require that carbon must be most electronegative, and we have seen here is the most strongly deactivated. This carbon is highly deactivated, therefore it can easily removable proton is available at second position, hence it can be removed. Compared to this 4 and 5 position, second position is the second position, proton can be easily, we can remove. Similarly, if your aim is to do some cyclodation reaction, here you see, if our aim is to do the cyclodation reaction, so we know reaction is taking place just like a furon. What are the positions? 2 and 5 positions, you see. 2 and 5 positions are reactive, you see here. If you take this oxygen, so this is a 2 position, 3, 4, 5 position, and there this what we say cyclodation or Diels-Alder reaction takes place, you can see it. So oxazole can act as a here a dinophile. Okay, this is a dine. So this is a dine and this is a dinophile. So this dine, where oxazole is a very good molecule which shows the furon type addition reaction, that is 1,4 addition reaction. Similarly, if our aim is to add methyl iodide on this azoles, our aim is to add methyl iodide on this azole. So where it will go? It methyl group is a when you ionize this, it form methyl plus CH3 plus. Therefore, their CH3 plus will always uh, taken by or will be attacked by the lone pair of nitrogen. Hence, we can say the azolium salts will form. Okay, 1,3 azolium salt. It can be imidazolium. It is here. It is given here. It can be imidazolium, or it can be oxazolium, or it can be thiazolium salts. So they have there are very much there are various type of uses applications of these. These are also called as ionic liquids. Okay, because they are liquids and they are ionic form. This is ionic form, and they are called as ionic liquids also. Fine. Okay. If our aim is to remove H plus ion, see here, sorry, our aim is to add H plus ion. Our aim is to add H plus ion. So where it will go? So it goes to both the heteroatom. It can go to this, first of all, this Z can be NH or O or sulfur, no problem. And it may goes to this NH also. So there is no problem in this. That may goes to this one. Also fine. Okay. Next point. Next point is again most important. This is again what the protonated azolium ion. Okay. Protonated azolium is imidazolium, isoxazolium, or thiazolium salts. Okay, fine. Now, if our aim is to remove the H plus from this molecule, so don't get confused. You cannot remove the NH, but only See, which is more acidic? See, second position is highly acidic compared to this NH. It's a very important reaction is this one. Okay, if you want to remove H plus, you will find that this NH proton is strongly bonded to nitrogen. इतना strongly bonded है कि you can remove this CH, or we can say CH is highly acidic in nature that compared to NH also. So remember, this is a very important point. This can be removed, okay, if our aim is to do the deprotonation of this azolium salts. So this is what is the idea, typical reactions involving 1,3-azoles as a precursor. Okay, fine. Now next point about the so like this, these are the reactions of 1,3-azoles which are giving the different products, and it is showing the reactivities also. So next part is what? The interesting part of the topic again. The second part of this compound about azoles is a 1,2-azoles. Okay, about the 1,2-azoles, and here there are only two compounds in your syllabus. Actually, there are three types of there are three 1,2-azoles. याद रखिए, तीन azoles हैं, जैसा कि हमने 1,3-azoles में देखा है ना, imidazole, thiazole, oxazole. Similarly, here also we have three types of azoles, 1,2-azoles, three types. But आपके syllabus में only two है given. It is a pyrazole and isoxazole. And isothiazole is also, but it is not included in your syllabus. Therefore, we are not going for that. So remember, pyrazole and oxazoles are included in your syllabus, and therefore we are discussing only these two. Fine. Fine. Now see, the most important about these 1,2-azoles is what? We'll go for their reactions first of all, then their preparations. The most important reaction is what? Concept about this. You know, 1,2-azoles means what is the meaning? It means that you see here, there are two heteroatoms in the ring which are directly connected. There are two heteroatoms which are directly connected. So what will happen? So the first point is their reactivity. Their reactivity. So now see, you see now you got it. If you see about this 1,2 position and 1,2 position is directly bonded heteroatoms. So see here, what is the concept about this? Direct linking of two heteroatoms has a very marked base weakening effect. Means you can understand in second sentence. Second sentence says that compare the ammonia with hydrazine. You see, and hydroxylamine. Compare the ammonia with the hydrazine and hydroxylamine. See pKa. You see, I have shown here bold one, bold script. pKa for ammonia is 9.3. Higher the pK, higher the basicity. We know this. You got it? Fine. And higher the pK, lower is the acidity or acidic power. The ammonia has pK 9.3, and that hydrazine having the direct bonding here. See, linkage, direct linkage between two heteroatoms. It has 7.9, means less basic compared to ammonia. And if you go to hydroxylamine, okay, I will tell you. If you go for hydroxylamine, again, there is a more heteroatom between strong heteroatom oxygen, nitrogen, and hence, again, basicity decrease. So there will be comparative questions. They can ask you, there are the pK, arrange the following compounds according to pK values, ammonia, hydrogen, hydroxylamine. If such questions are posted, so you should know the concept that direct linking of the two heteroatoms decrease the weakening the basic effect, basicity. So if they have given you three values and they have asked you arrange them, and they have given four options, so you should be very much clever about the idea that the heteroatom having no any other atom, only one heteroatom is there, that is more basic compared to this. See, this is the best example, and you apply this with the pyrrole, pyrazole, imidazole. See, try to understand this idea. So similarly, if you implement this, so we can say This is a mirrored in the 1,2-azoles. What is the meaning of mirrored? Means similar thing we can find in the 1,2-azoles. Fine. Fine. Pyrazole having the pKAH means, what is pKAH means? It is the pK means basicity with respect to hydrogen or acidity with respect to hydrogen on nitrogen. So if you see the pyrazole have 2.5 only. Pyrazole having the 2.5 while imidazole having, I think you should remember in the previous lecture we already discussed that. The pKa for imidazole is 7 almost, right? Around 7. And pK for pyrazole is 2.5. So which is more basic? Definitely imidazole is more basic. Why pyrazole is less basic? Because there is a direct bond formation between the nitrogen atom. You see pyrazole, fine, and hence we can say the pyrazole is a weak basic, then imidazole by how much time? Around 4.5 weaker than imidazole. Similarly, it is what we say pyrazole is weaker than isothiazole again by minus 0.5, and definitely isoxazole is minus 3.5. Okay, and some other compounds are also there. So definitely, simply we can say 1,2-azoles are weak based in 1,3-azoles. Simple. 1,2-azoles are 1,2-azoles are weaker based than 1,3-isomers or 1,3-azoles. The reason is what? Direct bond formation. Now let us go for the first reaction on the protonation. When you add proton H plus or HCl to pyrazole, so the nitrogen will take that H plus ion and it will form like this, and they undergo into resonance. So this positive charge distributed equally on the two nitrogens, and which makes the pyrazole more and more stable. Second reaction is about the oxidation at nitrogen. Okay, second is or oxidation simple. So when you go for the pyrazole oxidation in the by using the peroxide, okay, see here benzoyl peroxide we are using, room temperature, THF as a solvent, and sodium hydride to remove the proton. So what will happen? Nitrogen on nitrogen, there is an insertion. See, there is a nitrogen hydrogen bond. So this peroxide insert the hydrogen here and to become NOH. You can see. Okay. So only the reaction reported for pyrazole only. We can say isoxazole will not give this reaction. Remember. The third important reaction, very important reaction about managed reaction. You know this is the, remember the name pyrazole. This is the pyrazole. This pyrazole is a very important compound, heterocyclic compound or 1,2-azoles. When subjected for managed reaction, so we should know what is managed reaction. Managed reaction is a reaction between those compound which having the active carbon or active methane group, formaldehyde or any aldehyde which do not have a alpha hydrogen, and primary or secondary amine. These three compounds combine and they will form the managed product, managed base in the acidic condition. There are many reactions are available for managed reactions. So pyrazole is also a very important compound, and you can see here the reaction. So in pyrazole, the NH is highly acidic. When you add formaldehyde or benzaldehyde, we can take here no problem. And you take here as a pyridine as a base or primary or secondary amine. Okay. What will happen then? Heat it, you will find that here at this reactive site, you see at this reactive site, managed product will form. You see, very important. So we can say this is a nitrogen protected pyrazole product. See, nitrogen is protected. Now, one more example. Okay, so this is the starting material. If you take dihydropyran, and you add trifluoroacetic acid, same thing. So same thing will happen, and the dihydropyran means you should know that is dihydropyran. The structure is this is a pyran, And if you write double bond here, so dihydropiron. So this carbon undergo this carbon undergo into reaction, and the product is what? This is before you. What is the product? This is the product. So in this reaction, the second position of the pyran is attacked by the nitrogen, and hence this is the product. Question is, why there is no formation of bond with this three carbon, 1, 2, 3? The reason is that most stable carbocation should be formed. So once the H will release first of all to this pyran, H will go this position, third and second position acquired positive charge, that is stabilized by the oxygen, and hence second position is attacked by the nitrogen of the pyrazole. So very interesting reaction. Next, fourth reaction is about the acylation at nitrogen or acylation of pyrazole on different condition. Now see here. So acylation type reaction and acylation. So acyl group or phenyl sulfonyl group both can be reacted with the pyrazole, and depending on the condition, acylation takes place. It may goes to the nitrogen, it may go to the carbon also, definitely. Okay, and they will give you product. Fine. For example, you see this is the pyrazole, and you add acetyl chloride, and you take here benzene as a solvent at room temperature. No problem. Very simple reaction. So what we can find? You will find that this NH undergo acylation, and hence the product is this. Can you tell acylation is possible by using Lewis acid? Not impossible. Why? This nitrogen having NH bond will form the complex with the Lewis acid, and hence reaction will be locked, and hence though no Friedel-Crafts acylation is possible. Okay. Yes. Similarly, if you take some substituted pyrazole, it is a 1, 2, 3 tertiary butyl pyrazole, and definitely being aromatic compound, there is a resonance here. So this bond shift here, this bond shift here, and this NH become NH. So nitrogen NH can be at one position, NH can be at second position, no problem. Okay. Or in fact, actually, it is a 3 tertiary butyl pyrazole and it is a 5 tertiary butyl pyrazole. So see what is the number one? Always remember, number one always goes to the NH position, Okay. So when see here, when we, and it is NH, so one second number to next NH nitrogen, and third number like this, and 4, 5. What about this 1, 2, 3, 4, 5? Okay, 3, 4, 5. Okay, 3, 4, and this 5. Fine. So you got it? Yes. So remember, be clear cut. Have a clear cut idea about their nomenclature also. This is both are there in means they are interconvertible, and therefore this is called as 3, 3, 1, 2, 3, 3 bracket 5, 1, 2 azoles. When you do same acyl chloride and pyridine as it is, so this nitrogen definitely undergo to what the uh, acylation. It may go to this also, but due to the steric crowding, this compound react, and this will give. It means that see, whenever we have a pyrazole solution, so two compounds exist in that, but acylation takes place at where? At this carbon, because not as nitrogen, NH at this nitrogen. The reason is if it is going here, then there is a crowding, and hence compound will not be stable, and hence this is the product. Okay, because more stable product is formed in this also. So next reaction is what about cyanamide. It is again one special reaction of pyrazole. Pyrazole react with cyanamide. What is cyanamide? This is a cyanamide, NH2CN. Cyanamide. Okay. So again, it is an important reaction. And when you react this pyrazole with cyanamide in the presence of HCl, acylation type reaction takes place. And again, it produces N derivatives, nitrogen derivatives, that can be of very much great importance. From these derivatives, we can prepare guanidines. You see, so when you do Bock protection, see, slightly means, see, this is the first step is important for us. Remaining reaction are also possible. If you do Bock protection, so Bock protection will takes place at this nitrogen by using lithium hydride. and this Bock protection is over, then you add any amine attack, that amine attack here at its position. This bond break and pyrazole and again regenerated, and you can get this the different types of gonadines. Okay, it is a very interesting chemistry again to understand this idea. Fine. Yes. Next is what about the nitration? So nitration is a very well-known reaction. They can undergo directly pyrazole and isoxazole. They undergo straightforward nitration, and the position is fourth positions. Position is fourth carbon. Okay, right. Then what are the reagents for the nitration? Very remember, nitric acid is not working here. Okay. See, acetyl nitrate. If you see acetyl nitrate, it give nitrate and NO2 plus ions, nitration, nitrating